Hi everybody, I hope this video finds you well. In this video, which is the fourth part of what was supposed to be a three-part sort of series to go through section 4.2, introducing vector spaces, we're going to get to the sort of very last example that should have been in the previous video, but the last one was just getting a little too lengthy, so we had to add one more part here. So I do apologize, it was initially supposed to be a three-part video, now it's a four-part video to talk about these vector spaces. So, in the last video, we went through and we proved these 6 additional properties of vector spaces. Remember, these are not additional things you need to check to see if something is a vector space, but these are things that, if something is a vector space, must also be true. Remember, we also called special attention in the last video to properties 2 and property 5. These two sort of gave us a hint that in non-standard vector spaces, in vector spaces with non-standard operations, finding the zero vector and the additive inverses might be challenging. So the easiest way to do that is to find the zero vector using the multiplication by the zero scalar. And to find the additive inverses, it is easiest to use -1 as a scalar times, under scalar multiplication, the vector. So to do all that and to sort of put all this together in one example, we're going to do one last sort of big example going through and showing that a given structure is actually a vector space. And this structure, unlike the first one we did with P3 of R, which had all standard operations, is going to have some non-standard operations. So we'll see that we'll actually get to put some of these properties, namely property 2 and property 5 here, to use to help us understand this vector space. So let's go ahead and get started with that. So here's our sort of last example of doing everything from scratch. In later sections, like section 4.3, we're going to see that when we're operating inside of other vector spaces, we get to do a lot of stuff for free without having to prove everything from scratch. But right now, we're going to do one more sort of from the ground up sort of looking at a vector space here. So this structure that we're going to look at is going to be a pretty simple structure. It's basically just real 3 tuples, so it's vectors that are A, B, C, with A, B, and C all being real numbers. So it's just standard 3 tuples. But the thing that's non-standard here are the addition operation and the scalar multiplication operation. So the addition operation is defined here. It says that A1, B1, C1 plus A2, B2, C2 is actually A1 plus A2 minus 1, B1 plus B2 plus 2, and C1 plus C2. And the scalar multiplication, k times a1, b1, c1, is actually k times a1 minus 1 plus 1, k times b1 plus 2 minus 2, and k times c1. So some non-standard operations here. And we're going to show that this forms a real vector space, meaning a vector space with its field of scalars being the real numbers. So we've got to verify all 10 of those properties. Before we do that, though, let's just do our sort of standard definition at the beginning. We're going to need to have 3 sort of general vectors and 2 scalars. So let's just, for the sake of notation, let's let U be A1, B1, C1. Let's have V be A2, B2, C2. And let's have W be A3, B3, C3. Also, let's go ahead and let K1 and K2 both just be real numbers. And we'll use these definitions of U, V, and W, K1 and K2, throughout all 10 properties as we prove those. So let's go ahead and jump in starting with the closure properties. So property 1, closure under that vector addition. Now, the closure properties here should be very straightforward. If you think about it, even though you have these non-standard operations, all you're still doing is adding, subtracting, multiplying real numbers, which are always going to remain real numbers. So it should be very easy to show the closure here. So if we're trying to show closure, what do we need to show? We need to show that U plus V is an element of our vector space. So no matter what 2 vectors we start with here, if we add them, we remain in our vector space. Well, according to what we have here, U plus V, by this definition, is A1 plus A2 minus 1, B1 plus B2 plus 2, C1 plus C2. So clearly still a 3 tuple, and it doesn't really take any work to recognize that this guy here is an element of R. This guy is also an element of R, and this guy is also an element of R. So since all three components are real numbers, that means that it will still be an element of our vector space. So we're all good. We've shown that it's closed under addition. Not much to really do here, to be honest. Same thing, let's go ahead and do the closure under the scalar multiplication. So we need to show that if we do k1 scalar multiplied with u, that we will remain in our vector space. So let's talk about what k1 with u is going to look like. So we're going to be using this definition. So it looks like it's going to be k1 times a1 minus 1 plus 1, k1 b1 plus 2 minus 2, and k1 c1. Again, pretty clear. All of these, even though it's a little bit non-standard, are going to be elements of the real numbers, which guarantees that this thing is a 3-tuple of real numbers. So that guy is also in the vector space. So the closure here under these two operations, very clear. Let's get into talking about some of the addition properties. Okay, so we'll just notice we just have our operations defined above, so if we need to reference them, it'll be a little bit easier here. Let's go ahead and look at, before we do that though, we'll need a couple extra pages probably, so let's just go ahead and do that. Should have done that beforehand. Okay, that should be enough just in case. We don't know how many we'll need yet, but we'll get all those. So we've just got our operations defined up top, so it'll be a little bit easier. Okay, so for P3, we need to show plus is commutative. So we need to show that if we do u plus vector v, then that's the same as doing v plus u. Now, when we did this in our first example, when we were working with P3 of R, what we did is we sort of did a work from the left side and get to the right-hand side approach. That's fine. Just as an alternate way, I'm going to do these by doing a left-hand side, right-hand side, and then showing that they're equivalent. So just as a different sort of proof strategy here. It's the same idea, it's just a little bit different of a presentation. So what does the left-hand side here look like? Well, it would be this. Which according to sort of our definition there is going to be a1 plus a2 minus 1, b1 plus b2 plus 2, c1 plus c2. The right-hand side, on the other hand, is going to be v plus u, which is going to be a2 plus a1 minus 1, b2 plus b1 plus 2, and c2 plus c1. Now, keep in mind, in each component, the addition that's going on there is not vector addition. It's just normal addition or subtraction, so we can do that in whatever order we like. So this is clearly a1 plus a2 minus 1, b1 plus b2 plus 2, and c1 plus c2. And then we've shown that this guy here is the same as this guy. These guys are equal. So that's what we wanted to show. Okay, so we're all good there. We've shown that the left-hand side is the right-hand side, so we know that the plus operation is commutative. Let's go ahead and show that the addition operation is associative. So what do we need to show there? Well, we need to show that if you do u plus v, take the result of that and then add that to w, that is the same as starting with u and adding that to the result of v plus w. So once again, let's do a left-hand side, right-hand side approach. Left-hand side, u plus v plus w. What is that going to look like? Well, that's going to be a1 plus a2 minus 1, b1 plus b2 plus 2, c1 plus c2. That's going to be this piece here, and then we're going to be adding that to w, which is going to be a3, b3, c3. Now, how do we add these? Well, we know that according to the operation, what we're going to do is add these two, and then subtract 1, then add these two, then add 2, and then just add these guys as normal. So this is going to result in a1 plus a2 minus 1 plus a3 minus 1, b1 plus b2 plus 2 plus b3 plus 2, and C1 plus C2 plus C3. And again, that's just following, to get this, we're just following this definition here applied to this guy and this guy. Okay, let's go ahead and take a look at our right-hand side and see what we have over there. So on the right-hand side, we're doing U and then plus V plus W, where we're deciding to do the V plus W first. So that's going to be A1, B1, C1 plus, and if we add V and W, that's going to be A2 plus A3 minus 1, B2 plus B3 plus 2, and C2 plus C3. Then same operation, we add this, and then subtract 1, add this, and then add 2, and then add these guys directly. So that's going to be A1 plus A2 plus A3 minus 1 minus 1. And then B1 plus B2 plus B3 plus 2 plus 2. And then C1 plus C2 plus C3. Now, if we look at these, they are slightly different, but you can just tell that this versus this, well, this guy here and this guy here, they're out of order, but of course it's the same thing because this is really A1, A2, A3 minus 2. This is A1, A2, and A2, A3 minus 2. This guy is B1, B2, B3 plus 4, B1 plus B2 plus B3 plus 4, and these guys are identical. So once we've sort of done that, we can see that this guy here and this guy here, these guys are equal, and that's what we wanted to show, that the left-hand side and the right-hand side are the same, so we know that the plus operation is associated. Okay, nice. Now we're ready to move on to the really interesting ones, which is talking about the zero vector and the additive inverse. So let's go ahead and do that. So we need to talk about property 5. So we need zero vector here. Okay, so what is our zero vector? Well, now, just before we get into this, right, let's just make a quick note. So note, the zero vector is not this guy. How do I know that? Well, just try. If you do A1, B1, C1 plus 0, 0, 0, what actually happens? You get A1 plus 0 minus 1, B1 plus 0 plus 2, and C1 plus 0. And your result is A1 minus 1, B1 plus 2, C1. So you can tell here that if you use the traditional zero vector, that is not the zero vector under this non-standard addition. So how are we going to find that zero vector? Well, remember, way back from where we sort of started, we have that we can find the zero vector if we have a vector space by doing 0 as a scalar times any vector v. Now, that assumes that things are a vector space. So, in other words, the logic here is if something is a vector space, then this is true. We're trying to prove in our example that something is a vector space. So we can't just say, okay, this will work. But what we can do is say, let's see what this gives us and then confirm that that truly is the zero vector. So let's go ahead and do that. So what we're going to do is we're going to claim that the zero vector is going to be 0 scalar multiplied with A1, B1, C1. According to this definition of scalar multiplication, that is going to yield us 0, A1 minus 1 plus 1, 0, B1 plus 2 minus 2, and 0, C1, which is going to yield 1, negative 2, 0. So this is going to be our claim for our zero vector. How do we actually show that it is? Okay, so now we need to show that u plus that 0 equals u. So for any vector u, if we add it to the zero vector, then we're going to get our original vector. So let's check that. So A1, B1, C1 plus this zero vector, 1, negative 2, 0. What do we actually get? Well, according to this operation, we add the first two components, so A1 plus 1 and then minus 1, then B1 minus 2 plus 2, and then C1 plus 0. And what do we notice? That yields A1, B1, C1, which is exactly what we wanted. So we've now shown that this weird vector, 1, -2, 0, this is going to act as our 0 vector in this vector space with these non-standard operations. So our 0 vector is a little different than we would normally expect, but we do have one. All right, let's do the same for figuring out the additive inverse. Now I'm just going to see how many pages. Okay, so we've got plenty of pages to go here. All right, so P6, additive inverses. Well, how are we going to find the additive inverses? Well, they're going to be a little weird too, because of the weirdness of the 0 vector and the weirdness of the non-operation and of the non-standard addition operation. But keep in mind, we've got this guy right here that tells us if we do really have a vector space, then those additive inverses has to be -1 times the vector. So let's go ahead and make use of that here. All right, so let's claim that -u is going to be -1 with that vector u. So what does that actually give us? Well, -1 scalar multiplied with u is -1 scalar multiplied with a1, b1, c1. And let's use our definition of scalar multiplication to see what that comes out as. That looks like it should come out as -1, a1 minus 1 plus 1, -1, b1 plus 2 minus 2, -1, c1. Let's simplify that a little bit. That looks like it should come out as -a1 plus 2, -b1 minus 4, -c1. So our claim is that the additive inverse of any vector a1, b1, c1 is actually -a1 plus 2, -b1 minus 4, -c1. Now we need to show this. So we need to show that u plus -u is actually equal to the 0 vector. So let's go ahead and do that. U plus -u. What is that going to be equal to? Well, according to what we just wrote down, that's going to be a1, b1, c1 plus this guy here, -a1 plus 2, -b1 minus 4, -c1. So how do we do this vector addition? Again, using this operation. So we add the first two components, a1 minus a1 plus 2, and then we subtract 1. Then we add the next one, b1 minus 4, and add 2. And then we add the last two components just normally, c1 and minus c2. Let's simplify. This looks like we're going to get 1, -2, and 0. Well, is that the 0 vector? Yeah, right? That's what we just did here, that the 0 vector that we were going to use is supposed to be 1, -2, 0. And so with that 0 vector, we've just shown that u plus this -u that we came up with here really does give the 0 vector in this vector space. So notice it didn't come out as 0, 0, 0 because 0, 0, 0 isn't a special vector in this bizarre space that we're working on. The special 0 vector is actually -1, -2, 0. Okay, we've got some other properties now focusing on the scalar multiplication, so let's go ahead and do that. Now we got to talk about P7. P7 is the unit property. Unit property is very straightforward. We need to make sure that 1 with u is actually equal to u. Oh, let's put our need to show there. Sorry about that. Need to show 1 with u is actually equal to u. So let's do that. 1 with u is actually 1 with a1, b1, c1. So according to this definition, what we would do then, right, is we'd have 1, a1 minus 1 plus 1, 1, b1 plus 2 minus 2, and 1 times c1. Then let's go ahead and simplify these components. So looks like we get a1, and then 1 times b1 plus 2 is going to be b1 plus 2 minus 2. That's going to be b1, and then finally c1. And that, of course, is just equal to u. And there we go. So we've shown the unit property here, right? That if we scalar multiply by 1, then we get back to the original starting point. All right. Property 8, we have to show the associativity of this scalar multiplication operation. So we need to show that if we do k1 scalar multiplied with k2 scalar multiplied with some vector u, then that is the same as multiplying k1 and k2 just directly, and then taking the result and scalar multiplying that with u. Once again, this looks like it's going to be a little bit more complex because we're going to have to do a lot of operations here. So let's just go ahead and do a left-hand side, right-hand side approach again. So left-hand side, what is k1 scalar multiplied with k2 scalar multiplied with u? Well, we work from inside the parentheses, so let's do this. So that's applying this definition with k2. So this is going to be k1 scalar multiplied with parentheses. And then we should get what? K2, A1 minus 1 plus 1. K2, B1 plus 2 minus 2. And K2, C1. Okay, and then we'll just close that up there. Okay, and then what can we say about this? Well, we now apply this scalar multiplication where we're going to multiply this guy onto each of these, treating this entire thing as the A, this entire thing is the B, this entire thing is the C. So it's going to be a little bit messy, but we can do it. Big set of parentheses. We're going to have K1, parentheses, whatever was here, minus 1. So that's going to be K2, A1 minus 1 plus 1 minus 1. Close that parentheses up, and then you have to go ahead and add 1 at the end. Okay, then we're going to have K1, parentheses, whatever was here, but we're going to add 2 to it. So K2, B1 plus 2 minus 2 plus 2. And then at the end of all that, we subtract 2. And then last one, always the easy one, we just multiply directly. So we get K1, K2, C1. Okay, now, before we get to the right-hand side, notice that some of these do clean up pretty significantly. We should see this as K1, K2, A minus, A1 minus 1, and then those ones cancel out plus 1. This guy should be K1, K2, B1 plus 2. The minus 2 and the 2 right here cancel out. So we can just close that up, minus 2, and then K1, K2, C1. Okay, let's go ahead and check out the right-hand side. So right-hand side, we're going to be working with this guy right here. So K1, K2, scalar multiplied with U. So that means just instead of having K here, here, and here, we're going to be using K1, K2. So that looks like it's going to be K1, K2, A1 minus 1 plus 1. Then K1, K2, B1 plus 2 minus 2. And K1, K2, C1. Are these things the same? Well, this guy here, if we just dropped some parentheses, then this here is the same as this guy here. This here is the same as this guy here, and this guy is the same as this guy here. So these two things, this vector here and this vector here, these guys are equal. That's what we wanted to show. Okay, we're down to just needing to do the distributive properties here. So let's go ahead and do those on this page here. This is our last one, so just in case, let's add one more onto that. All right, P9, right? Distributive property. We need to do scalar multi over vector addition. So what do we need to show here? We need to show that if we take a K1 and have it distribute over U plus V, then that is going to be the same as doing K1 scalar multiplied with U, vector addition K1 multiplied with V. In other words, that we can distribute this guy onto these two pieces. Once again, let's do a left-hand side, right-hand side approach. So left-hand side, K1 U plus V. Again, working from inside the parentheses first here. So we know that that's going to be K1 scalar multiplied with, according to this operation up here, A1 plus A2 minus 1, B1 plus B2 plus 2, C1 plus C2. Okay, and then we're going to distribute this guy onto these. So that looks like it's going to be parentheses K1. Then we take 1 away from what was in here. So A1 plus A2 minus 1 plus 1. And then on this guy, we do the same, except we're going to add 2. So this guy looks like it's going to be K1, B1 plus B2 plus 2 plus 2. And then we subtract 2. And finally on this guy, we just get K1, C1 plus C2. Okay. Now let's go ahead. If we want, just in preparation, we can take a look at maybe what this looks like a sort of bit clearer, and just to maybe simplify things so that we can see it. We could do that later too. So let's just go right to the right-hand side. But considering that this is still pretty messy, I am going to just leave myself some space here in case we need to look at it a little further. Right-hand side, we need to look at K1U and then plus K1 with V. So let's go ahead and take a look at what those are going to look like. This guy is going to look like K1, A1 minus 1 plus 1, K1, B1 plus 2 minus 2, and then K1, C1. And then that's going to be vector added to this guy, which is going to be K1, A2 minus 1 plus 1. K1 B2 plus 2 minus 2, and then K1 C2. Then we're going to need to vector add these guys according to this here. So we would do that and get a result of K1 A1 minus 1 plus 1 plus K1 A2 minus 1 plus 1 minus 1 overall. You know what? This is going to be pretty lengthy, so let's go ahead and scoot this back here. So this is going to equal here. So again, we'd add these two components, but then subtract 1. So K1 A1 minus 1 plus 1 plus K1 A2 minus 1 plus 1 minus 1. We'd add these two and then add 2. So it'd be K1 B1 plus 2 minus 2 plus K1 B2 plus 2 minus 2 plus 2. And then, according to this, we just add these guys directly. So K1 C1 plus K1 C2. Now, these two things don't necessarily look too similar, but let's do a little bit of clever factoring. On this guy, let's factor out the K1 from these guys, and let's clean up the 1, 1, and minus 1 to being just a plus 1. So that looks like we could write it as K1 A1 minus 1 plus A2 minus 1, and then all that would simplify to just a plus 1. Here we do K1 B1 plus 2 plus B2 plus 2. Then we have a minus 2, and a plus 2, so minus 2. And then here we just factor out the K1, C1 plus C2. Okay, now quick inspection. This here, same as this guy here. This here, same as this guy here. This guy here, same as this guy here. So these two things, this guy and this guy, these are equal, which is what we wanted to show. All right, we're in the home stretch. Just last one. Got to do property 10 here. So P10, we need to do distributive property, scalar multi over scalar addition. So what do we need to show here? Well, we need to show that K1 plus K2, scalar multiplied with U, is the same as K1 scalar multiplied with U, and then vector added to K2 scalar multiplied with U. So left-hand side, again, K1 plus K2, scalar multiplied with U. So we're going to be using this definition, but with the K being K1 plus K2. So it looks like we should get K1 plus K2, A1 minus 1 plus 1, then K1 plus K2, B1 plus 2 minus 2, and then K1 plus K2, C1. Okay. Now again, we might need to simplify these, so we'll give ourselves a little bit of space. We'll move down here to do the right-hand side. So let's go ahead and do K1 U, and then vector added to K2 with U. So let's go ahead and do these. What does this guy look like? Well, that looks like it's going to be K1 A1 minus 1 plus 1, K1 B1 minus B1 plus 2 minus 2, and then K1 C1. And then that is going to be vector added to this guy here, which is going to be K2 A1 minus 1 plus 2 plus 1, K2 B1 plus 2 minus 2, and K2 C1. Okay, now we add these guys and then subtract 1. We add these guys and then add 2, and then we just add these guys directly. So this is going to result in K1 A1 minus 1 plus 1 plus K2 A1 minus 1 plus 1 minus 1. Then K1 B1 plus 2 minus 2 plus K2 B2 plus 2 minus 2 plus 2. And then plus 2. And then finally K1 C1 plus K2 C1. So we can do a little bit of clever factoring again. We can take the A1 minus 1 from these guys and then also clean up the 1s here. So it looks like that should become K1 plus K2 times A1 minus 1. Then we had a plus 1, and a minus 1, so plus 1. Then on the next guy, same sort of factoring, K1 plus K2 times B1 plus 2. Then we had a minus 2, and a plus 2, so that becomes a minus 2. And then finally, just K1 plus K2 times C1. What do we notice there then? Well, this guy here is exactly the same as this guy here. So we've shown that this is equal to this. All right, so that showed that this crazy space, even though it resembles and has the same objects as standard R3, it had these two totally non-standard operations. Despite the fact that it had these two non-standard operations, despite the fact that the 0 vector turned out to be 1, negative 2, 0, it still is a vector space, and it still acts just like any other vector space. Now, to be honest, these types of vector spaces with non-standard operations are incredibly important and incredibly interesting in theoretical mathematics because they're telling you that the structure that we have can be adapted into all these different types of crazy structures. We're personally not going to use non-standard operations very much because our end goal is to get back to working with sort of standard matrix operations, standard systems of equations, and eventually standard differential equations. So this example is supposed to get you guys sort of comfortable to the idea that other operations can be defined that act like addition and scalar multiplication. But to be honest, except inside this section introducing you to the concept of vector spaces, we are not often going to see non-standard operations. But wanted to go through at least one full example of that. In the next section, section 4.3, we're going to see how much easier things are when we're working inside spaces that we already know are vector spaces.